All right, this is Honors Algebra 2 Pre-Calculus. We're doing section 9.6 in Pre-Calc, which is counting principles. So we're going to lead off with the fundamental counting principle, which is sort of the big one to start with. So it sounds really complicated. It's not. I'm going to read you what the textbook has on page 663, and then I'm going to walk you through what it means logically. So let E sub 1 and E sub 2 be two different events. If E sub 1 can occur in M1 different ways, right, and after E sub 1 is done, E sub 2 can separately occur in M2 different ways, then the number of ways E1 and E2 can happen together, like overall, is M1 times M2. So let's talk about the logic of this for a sec. So let's say that I have 2 shirts and 3 pairs of pants, right? So if we're talking about the ways that I can get dressed with my shirts and pants, right? So I could have let's just we're gonna call my 2 shirts shirt 1 and shirt 2 because I'm lazy. So I could wear shirt 1 or I could wear shirt 2, right? But then once I put shirt 1 on, right? After I put shirt 1 on, I have 3 different options for pants, right? I could wear like my shorts, or I could wear like long pants, or I could wear my jeans, which look a lot like long pants, but we're just going to pretend that they're different because we'll make them blue, okay? So, but I could have those same 3 options, my shorts, or my like long dress pants, that doesn't look like pants, or my jeans, right? I could have the same 3 options if I had worn shirt 2. So what ends up happening is I had 2 different options for shirts and 3 different options for pants, and if you count, I have shirt 1 and the shorts, that's 1 option, right? Shirt 1 and the long pants, that's 2 options. Shirt 1 and the jeans, that's 3 options. Shirt 2 and the shorts, that's 4 options. Shirt 2 and the long pants, that's 5 options. And shirt 2 and the jeans, and that's 6 options. So I end up with 6 total options for how I could get dressed. But the reason that I end up with 6 is because for my first event, or my first thing that happens, my shirt, I had 2 options, times for my pants, I had 3 options, and 2 times 3 is 6. Ignore the very old, wonderful dog coughing in the background. Sorry, Bales. You're my wonderful old man. All right, so fundamental counting principle says that I have 6 options. So this is called a tree diagram. I mean, you don't have to do it with the pictures of the shirts and the pants, certainly. But tree diagrams are great when you're younger, in like elementary or middle school. But as math gets harder and as the numbers get larger, a tree diagram is not really a practical version of this problem. And it's a lot easier to get the fundamental counting principle. So now that fundamental counting principle leads us to some other stuff that we're going to get to in a sec. So yes, that's the basics. Let's do an example with the fundamental counting principle. Okay, so example 1. Okay. You have, okay, so you're going to fill your backpack. So you need to put stuff in your backpack. Maybe you're packing for a trip, who knows, but maybe you're packing and you're not a really discerning packer. Totally fine, okay? You have 3 books, 4 binders, 10 pens, and we'll say books, binders, pens, and we'll say 2 notebooks, okay? Okay, how many ways can you put one of each in your bag? So what I'm saying is that when you're done packing, your backpack should have 1 book, 1 binder, 1 pen, and 1 notebook, right? So if you were to make a tree diagram of this, it would take you a ridiculous amount of space and it would be generally awful, right? So essentially what we want to say is, oh hey, how many different ways can I pick the book? Well, I have 3 options for the number of books. How many different ways can I pick the binder? Well, there are 4 different binders, right? How many different ways can I pick my pen? Well, there are 10 different pens. And how many different ways can I pick my notebook? Well, there are only 2 different notebooks. So using that fundamental counting principle, it's going to be 3 times 4 times 10 times 2, right? Which is 12 times 20. So 12 times 2 would be a 24, right? So 12 times 20 is a 240. So there are 240 ways. Now you can imagine if you made a tree diagram of this, it would be absolutely awful, right? Just no fun at all. So that's kind of our first example. Let's do a second example while we're at it, because this is a fairly short video, so we'll do a second example. So example 2. you roll a die, and we're talking like a normal 6-sided die, right? So the normal like 6-sided, none of your awesome like D20 D&D stuff. So you roll a 6-sided die and flip a coin. How many outcomes are there? Right? So now this is one where you can actually do this pretty logically with a tree diagram, but if you think about it, I roll a die, right, which has 6 possible outcomes, right? 1, 2, 3, 4, 5, or 6, times I have a coin, and the coin only has 2 possible outcomes, heads or tails, so there are 12 possible outcomes, right? If I wanted to know how many different outcomes there are 12. Now this is one that you could actually make a tree diagram for pretty easily, because you could say, hey, I have a 1 and I could either get heads or tails, or I have a 2 and I could get heads or tails, and I have a 3 or I could get heads or tails, and you could do this all the way down until you get to 6. I'm just kind of lazy. So you get down to 6 and you get heads or tails, right? So you could make a tree diagram for this if you wanted. Or similarly, you could start with flipping the coin first and say heads could be 1, 2, 3, 4, 5, 6, and tails could be 1, 2, 3, 4, 5, 6. So meaning one outcome is 1 and heads, and another outcome is 1 and tails, and another outcome is 2 and tails, and another outcome is, 2 and heads, and then 2 and tails, and so on.